Welcome back, everybody. In this video, we'll be continuing with section 4.1, working on exponential functions. Our first two examples here are actually creating an exponential function that contains a couple of points. So these are from our textbook. We're going to be doing numbers 18 and 21. So as you recall, the format for an exponential function looks like f of x equals ab to the x power. B is the base, a is the initial value. So for 18, here it says, for the following exercises, find the formula for an exponential function that passes through the points given. So what we'll do is this. So we know that our function should be ab to the x power. We're going to substitute in the x, and that's going to have to equal the y. So f of 0, which is ab to the 0, is a times 1, or a, that has to equal 6, right? When the input 0, the output 6. That's what the fact that the point 0, 6 is on the graph of the function. So this tells us that the a is 6. So what I've got so far is that f of x equals 6b to the x. 6b to the x. And so we'll use the second point to figure out what b is. So we know that f of 3 has to equal 1. Since f of 3 has to equal 1, f of 3 is equal to 6 times 3, b cubed, right? X is 3. That has to equal 1. Okay, and so, sorry, I'm using the wrong point. I used the 3, 1 here instead of the 3, 750. Sorry, I should have been more careful. So the other point is 3, 750. The output there is 750, not 1. Okay, so that's going to be 750. So not 3, 1. We're doing 18. All right, so f of 3 is 750. So 6b cubed is 750. If 6b cubed is 750, we can divide through both sides by 6 and get b cubed is 125. And so from there, we'll have that b is equal to 5. Okay, now we have both a and b, so we're ready to write down our complete function. Our f of x is equal to 6 times 5 to the x. Okay, and that's our function for 18. So let's try 22 next. We're going to do the same basic thing, but just two different points. So again, this time f of 3 is equal to 1. Our function is supposed to look like ab to the x. Since we know f of 3 is equal to 1, we'll have f of 3 is a times b to the third power. Our x is 3 here. And so that is supposed to equal 1. So we have ab cubed equals 1. That's one fact about a and b that we know. And then for 5, 4, we have f of 5 is equal to 4. And f of 5 is a b to the fifth power, and that's supposed to equal 4. Okay, so we have two equations that involve a's and b's, and so that's a system of equations that we can solve. So how I'm going to do this is I'm going to solve each of these for a. Actually, let me just solve the first one for a. So a has to equal 1 over b cubed. Okay, if a is 1 over b cubed, then I'm going to take and substitute that into the second equation. ab to the fifth power equals 4. I'm going to replace that a by 1 over b cubed. Okay, and then we'll solve for b. So 1 over b cubed times b to the fifth power, that's b to the fifth power over b cubed. And so we'll end up with b squared equals 4, so b equals 2. Here, notice that it's not plus or minus 2 because the base for the exponential function always has to be positive. Okay, so the b here is going to be positive 2. And then once we have b, we can start working our way back to find a. A is 1 over 2 cubed, and so that is 1/8. So putting together the pieces, our f of x is going to be A, which was 1/8, and then our B was 2, so 1/8 2 to the x. Okay, all right, and that finishes that. Okay, so what these kinds of questions remind me of is it's like the exponential function version of the kinds of questions that we've done before, where we were to find the equation of a line that passes through 2 points. Like if I told you like that I had a line that passed through the points 1, 5, and 8, 11, then I know that you could figure out the slope. We did this quite a lot. You could find the slope and then substitute that into the equation of the line and come up with the y-intercept, and then we'd have the complete equation of the line. Here we're doing essentially the same thing, only it's not a linear function that we're finding, it's an exponential function that we're finding. Okay. One of the bigger applications of exponential functions that we'll consider is the idea of compound interest. So let's talk about interest first, and then we'll make it specific about compound interest. Simple interest, well, interest first. Interest is a fee paid for the use of money over time. If you put your money in the bank, they have it to use to lend people to buy houses or whatever else people may want to borrow money for. And while you don't have your money because it's in the bank, you can't spend it. And so they pay you a little tiny bit of interest for that privilege. On the flip side of that, if you borrow money from the bank or from a credit card company, you have it to spend to buy your school books or food or whatever. And since you're using somebody else's money, when you pay it back, you have to pay it back with interest. That was the fee paid for use of money over time. There's basically two ways to calculate interest. There's simple interest and compound interest. Simple interest, the amount of interest is figured out one time over the course of the borrowing period. And the formula for that is I is the dollar amount of interest, P for principal, R for the interest rate, T is time. The principal is the amount of money borrowed. If you think about it, if you borrow $20 from your cousin for the weekend, then you should pay less interest than if you borrow $2,000 from your cousin for the weekend, right? Because it's less money. So principal is one factor that enters into the calculation of interest. Notice, by the way, that the word principal here in this context is P-A-L, principle, not the P-L-E, principle, like somebody's principles, things they believe in. It's the different version of the word, P-A-L, principle. Okay, the interest rate, how much interest you're charged. As I had said, if you have a savings account with a bank, you're going to have a really small interest rate. If you have a mortgage for your house, it's probably somewhere between 3 and 6%, depending on when you bought it. And if you have a credit card, the interest rate might be 18 to 24% or something. The interest rate is basically the fee or one factor of the fee component that is makes up interest. And that is basically determined by usually the lender or whoever has the most power. Typically, it's the bank. Okay, time, how much time do you have the money for? If you're going to borrow $20 from your cousin for the weekend, then you're not going to pay as much interest as if you pay, or as if you borrow the $20 for 6 months. Okay, so that's the other factor. And so to figure out simple interest, you just multiply the principal times rate times time. So suppose that we're doing the lending this time. Suppose that you lend $1,000 at 10% annual interest to your cousin or someone for 3 years. We want to know how much is owed at the end of that time. So interest is principal, that's the 1,000, times the rate, which is 10%, times the time, which is 3 years. 1,000 times 0.10 is 100, times 3 is 300. Okay, so that would be the dollar amount of interest. Of course, you'd want to get paid back your $1,000 too. So the amount to pay back would be 1,000 of principal, plus the $300 in interest, or a total of $1,300. Okay, so that would be the answer to the question. How much is to be owed at the end of that time? $1,300. There's another formula for interest that gives that kind of future value, not just the amount of interest. If you take up here in the upper right, if you take the principal, which is the amount borrowed, and then add to that the interest, which is principal times rate times time, you get P plus PRT, right? And that's the principal plus the interest. If you factor the P out, you get P, principal, times 1 plus the rate times the time. So that's a formula for the future value, not that is like the balance that is owed, not just the dollar amount of interest. Okay, so that's what simple interest is about, and it doesn't really have much to do with exponential functions, which is why we're here today. But the other way of figuring out interest does have to do with an exponential function, and that's compound interest. The idea for compound interest is this. Let's say that we take a look at this $1,000 that you've lent for 3 years. We've already figured out that the person owes us $1,300. Okay, let's say that we only lent the money for 1 year. So if it had been 1 year, then how much interest would be owed? Well, it's 10% per year, right? So 10% of 1,000 is 100. So it would be 1,100, right? Because it's 10% every year. 10% is 100. So 100 every year for 3 years was where we got that 1,300 from. So if it was for 1 year, then it's only 1,100. So one way of looking at this loan that we made, $1,000 for 3 years, is didn't they kind of owe us 1,100 after that first year? So in years 2 and 3, we basically gave them a free ride on that $100 worth of interest. What if instead we start charging them interest on this $100, not just the $1,000 in principal? Also, in year 2, there's another $100. So they owed us $1,200 after 2 years. And so that $200, let's charge them interest on that also. So that's the idea that compound interest is based on. And so let's see if we can see that in more detail. So instead of figuring out that interest just once, let's figure out the interest every year and add it to how much they owe us. So after year 0, that is when we first make up the loan, the person owes us $1,000. Okay, after 1 year, we call them up and say, okay, it's been a year, are you going to pay us back? No, okay, we'll try again next year. So they owe us $1,000 that they originally borrowed, plus 10% of that 1,000. That's our 10% interest. So that's 1,000 plus 100. Or 1,100, which we knew, right? It's $1,100 after 1 year. The thing is that after another year goes by, we want to know, okay, are you paying back? No, it's going to be another year. Okay, now when we go to figure out the interest, it's not just going to be 10% of the 1,000 that was originally borrowed. It's because now they owe us 1,100. So the new principal is 1,100. So we'll take 1,100 plus 10%, not of 1,000, but 10% of 1,100, and that's $110. So they owe us $1,100 from the prior year, plus now 110. $100 that they'd originally borrowed, that gives, or from that 1,000 that was originally borrowed, plus $10 interest on the first year's interest. So now they owe us 1,210. Of course, you can guess where this is going to go now. Year 3, they don't just owe us 1,000 or 1,100, they owe us 1,210. So their starting balance this year is 1,210. We're going to add to that 10% of 1,210, and that's 121. And so altogether we'll have 1,331. So I realize that $31 extra over 3 years doesn't seem like a lot, But the point is, we wanted to understand the idea. And also, the amount of interest that was originally earned in the first place was only $300. And so we've increased the interest that was earned from $300 to $331. So the amount of interest earned over the whole period of the loan is 10% higher by figuring out the interest every year. So hopefully that makes total sense. I want to think about what a formula for this would be. Let's say that we wanted 25 years or 26 years, right? We don't want, you and I both don't want to see me write this out like, 22 more times. So let's see if we can notice the pattern that is occurring here. And we saw this kind of with our population example way earlier. So coming back up to our first row, we had 1,000 plus 10% of 1,000. We could look at that as 1 plus 0.10 multiplied by 1,000. And that's 1.10 times 1,000. Okay, and then in the second row, we have 1,100 times 1 plus 0.10. So again, we'll factor out the 1,100, and that leaves 1.10. And then for the last row, I'm sure you can do this, we'll have 1 plus 0.10 times the 1,210. And so you can see what's happening here is that instead of multiplying by 0.10 and then adding, what we can do is just multiply by 1.10. Okay, and so if we want to know this done into the future, what we can do is just repeatedly multiply. And how do you do repeated multiplication? You do repeated multiplication by raising to a power, which is our exponential function. So to do 25 years, then this would be, let me do it the wrong way first for a second. If this would be 1,000 plus times 1.10, that's after 1 year, 2 years, 3 years, 4 years. I said I wasn't going to do this. This would be how many years? We're multiplying together by 1.10 to the 25th power. So this would be 1,000 times 1.10 raised to the 25th power. And then for one more year, it's 1,000 times 1.10 raised to the 26th power. So let me give you some numbers for this. So this first one is 108,3471. And then 11,918. 18. All right, so we can see that the balance is going up over time, and it's achieved by repeatedly multiplying. Okay, so that's the basic idea for compound interest. Of course, we have more coming. All right, so a natural next question is this. In the first year, we were thinking, okay, well, the person owes us $1,000, and that's the 10%. They owe us $100 from borrowing that $1,000 for the 1 year at 10% interest. And so that's why we charged them interest on that $100 during year 2. But if you think about it, if they owed us $1,100 as the total balance after 1 year, and that was $100 of interest in 1 year, then does it make sense that after 6 months they owed us $50? That is, if it's $100 a year, then a half year, which is 6 months, would have been $50. So how about we figure out the interest every 6 months? Because we kind of are letting them take a free ride on that interest that is accumulating over the course of that first year. So let's figure out the interest more often. And if you figure out the interest more often, we're not going to go through the development of the formula for this, but it goes like this. The formula that we're working with so far, the amount of interest is the principal, 1 plus the interest rate raised to the power of how many years it is. Okay, so you could see that fits what we've done before. The R was 0.10, the T was our time, P was the $1,000. This is going to be for annually. Okay, if we figure out the interest more often, like every quarter or every 6 months or every day, then how would that look? So the formula goes like this. It's still A equals P for principal, 1 plus the interest rate divided by N. I got to tell you what N is, raised to the N times T power. So the T, the P, and the A, and the R are all familiar. N is the number of compounding periods, and that reflects how often you're figuring out the interest. So 12 for monthly, 4 for quarterly, 52 for weekly. How often are you figuring out the interest? That's the number of compounding periods. So basically, if you compare this to the previous formula that we had, we're taking R and replacing it by R over N. So we're turning that into what's called a periodic rate. And instead of T, like as T total years, we're having N times T, which is our number of compounding periods. So let's see an actual live example of that. So let's go back to our $1,000 10% interest problem and figure out the interest monthly. And we'll see what that future value is going to end up being. So let me first set up our calculation. So our amount will be our $1,000. Sorry, my pen's got a little wonky. And then that will be 1 plus 0.10. Sorry, I need to change my battery. Hang on a second. All right, so let's try that again. So our future amount is going to be 1,000. Let me rewrite the formula first. Principal, 1 plus R over N raised to the NT power. So for this one, our principal is still $1,000. It's 1 plus, and then R over N. Our interest rate was 10%, but now the interest is figured out monthly. So that's 12 times a year. And then in the exponent, it will be N, that's 12 times a year for 3 years. So what's happening is that exponent is now 12 times 3, or 36, because we're figuring out the interest 36 times, but our interest is now 0.10 over 12, which is 0.008, so a little less than 1% per month. Okay, so let's go ahead and calculate that. And then that's raised to the 36 power times 1,000. All right, so 1,348 and then 18. So 1348.18 if we figure out the interest monthly for 3 years. Okay, so then again, a natural question is, well, what if we do it more often? You know, why don't we do it daily? So just for fun, let's go ahead and see what it looks like if it's daily. So fortunately, it's a relatively small modification to the problem. It'll be 1,000, 1 plus 0.10, that's our interest rate again. Now it's divided by 365 because there's 365 days in a year. And then in the exponent, we'll have 365 times 3. Okay, your calculator might have a little trouble with an exponent of that size, but we should be okay. If you have trouble with it, let me know. More on that in a little bit. All right, so 1349.80, which brings up itself something kind of interesting. So we saw that our initial amount of interest was $1,300. So by figuring out interest, okay, it's $1,300. If we figure out the interest every year instead, we saw that it's going to go up to $1,331. Okay, if we figure out interest annually, it jumps from $1,300 to $1,331. Okay. And then if we went to monthly, we saw that it goes to 1348.18. Let's see, this is annual, monthly. If we go to daily, we saw that it only ends up being 1349.80. So it's going up, right? If you figure out the interest more often, it's going up, but it's not like you're going to get an infinite amount of money doing it infinitely often. Increasing the compounding frequency increases the amount that you get, but by less and less. To go from just once to annually, you got $31 more. To go from annually to monthly, you picked up like $7 and change. To go from monthly all the way to daily, right, 30 something times as often, you only picked up like $1, around $1. So increasing the compounding frequency does increase the amount, but by less and less. All right, so that's it for this video. We do have more examples coming up. In the meantime, let me know if you have any questions, and have a great day.